Hi, I am Kaushik from Group 12. This presentation outlines our approach to building an ML-driven system to detect and prevent credit card fraud transactions. With rising fraud cases impacting both revenue and customer trust, a scalable, accurate, and compliant solution is essential. I'll walk you through the business context, analytical process, model outcomes, and strategic recommendations aimed at safeguarding transactions while maintaining user experience and compliance. Credit card fraud has significant consequences when it does occur, even if it's minimum. It leads to financial losses, operational strain, and reputational damage. Traditional detection methods like manual review and rule-based systems are not scalable for modern transactional volume. A reliable and an automated system is crucial to stay ahead of evolving threats while protecting customer trust. Our goal was to develop a robust and an efficient system capable of detecting fraudulent credit card transactions in near real time. The system needed to be highly accurate, minimize false positives, operate at a large scale, and comply with regulatory and ethical standards. This aligns with broader goals around customer protection, risk reduction, and digital transformation. We used a publicly available dataset on Kaggle containing nearly 285,000 credit card transactions over a period of 2 days, including both legitimate and fraudulent cases. Fraud accounted for only 0.17% of the total transactions, highlighting a very high and a significant class imbalance that makes the detection challenging. The data was anonymized and secure, and it also allowed us to identify behavioral patterns indicative of fraud without compromising on any kind of privacy. Special care was taken to handle the class imbalance to help with accurate and reliable reporting. Several approaches were tested to detect fraud effectively. As mentioned earlier, rule-based systems and manual reviews either proved too rigid or resource intensive. Ultimately, advanced machine learning models, specifically ensemble models, were chosen due to their high performance, their ability to handle class imbalance, and scalability. The focus remained on building a solution that is fast, accurate, adaptable, and scalable. The selected model performs well across key performance indicators. It detects over 90% of fraudulent transactions, maintains more than 97% overall accuracy, and minimizes false positives to fewer or less than 2 to 3 in around 1,000 legitimate transactions. These results confirm its suitability for real-time fraud prevention and detection, striking a balance between security and customer convenience. The system significantly reduces fraud-related losses and improves operational efficiency by automating detection and prevention. It also enhances the customer experience by minimizing false alerts. With audit-ready tracking, the model supports compliance with financial regulations. In essence, the solution adds value by protecting both the reputation and organizational values. We recommend a phased rollout beginning with the pilot deployment. This will allow us to test the system in a controlled environment, monitor its performance, and make necessary adjustments. As results are validated, we can expand its application across more transaction types and different segments, while still ensuring governance and accountability remain in place. Responsible use of machine learning and AI is a core priority as well as a principle. Measures are to be implemented to prevent discrimination, to ensure fairness, and also to maintain transparency in how fraud is flagged. Human oversight remains very crucial for high-risk cases and cannot be overlooked. The goal is to deploy technology that is as fair, and explainable as it is effective and efficient, preserving trust at every step of the way. Utmost care should and will be taken to fully align with data protection and financial industry regulations, including GDPR and PCI DCSS. All data used will be anonymized and securely stored. We recommend continued oversight to ensure evolving compliance standards are met as the model is scaled and refined in production environments. We have also identified potential risks and outlined strategies to manage them effectively. False positives are reduced through threshold tuning and human reviews. Regular model updates addresses potential drift. Encryption and restricted access are very much required to protect data. Ethical risks are managed via governance oversight. These measures ensure a balanced as well as a responsible deployment across the pilot and future segments. Our machine learning powered fraud detection system offers measurable business value, reducing loss, improving customer experience, and supporting compliance. It is technically ready and operationally feasible. The next steps include piloting, monitoring, deploying, and scaling the solution. With this solution, we can transform fraud prevention into a proactive, automated, and an effective function. With this, I have finished the presentation. Thank you for your time.
Thanks for explaining that, Koshik. It was really insightful. Hi everyone, my name is Vinay Mittal. I'll be continuing here with the code piece which we have framed around the business use case, which Koshik has just explained. So this data set was uh, collected and analyzed during a research collaboration of Worldline and the machine learning group of University of ULB. They were doing some research on big data mining and fraud detection, and also have uh, made their project available on researchgate.net under the name fraud detection dash 5. So I just want to take a moment and cite them about the data set. Now we could easily find this data set on the Kaggle, which is why we have utilized the Kaggle Hub library, and we have cited the specific name and downloaded it from there. The moment followed by download, we just want to make sure that the version control of the libraries are same, just to be on the same page. The moment we do that, we have also imported the required library, which we'll be seeing in coming seconds. The moment we have imported the required library, uh, we just read the CSV, which is the credit card CSV, right, which we have downloaded above here. As you can see in the df.head, we have a numerous column here. There's this time column, then there's from V1 to V28, then the amount column, and then there is the target column called as class. Now you must be wondering, what does this V1 to V28 are referring to? Um, Firstly, this whole data contains only numerical input variables, which are the results of the PCA transformation, the principal component analysis. And this dataset consists of transactions made by credit card in September 2013 by European card holders. So this dataset represents transactions that occurred in 2 days, where we have 492 frauds out of 284,807 transactions. So the dataset is highly unbalanced. The positive class frauds accounts for 0.172% of all transactions. And talking about the features V1 to V28, as I mentioned that uh, this is the result of PCA transformation. So we, not we, but the university ULB have labeled them from V1 to V28. And The only features which have not been transformed with the PCA are time and amount. The feature time contains the second elapsed between each transaction and the first transaction, and the amount is the transaction amount. The class, as I mentioned, is the response variable, and it takes value 1 in case of fraud and 0 otherwise. So walking through next, we have information to see if there are any null values and to check if there are any missing values. So far we have just downloaded it, loaded the libraries, see inspected it, how the data is performing. And as I just mentioned that there is a highly imbalance. Here is what we are seeing in the graph as well. And some more graphs around the transaction amount and the time. So as we know, we have the class imbalance. To overcome with, we have various resampling techniques with undersampling and oversampling. A particular sophisticated and widely used oversampling method is the synthetic minority oversampling technique called as SMOT, which is what we used here. And there's a standard library which we can utilize to do that. There is a whole statistics behind how they do it. In the interest of time, I'll just show you how before the SMOT there was this imbalance in the data set, and post that we have fixed this. Moving on to the feature selection, which is the most critical aspect in any machine learning data science problem statement. We have tried feature selection using random forest with the top 12 20 features, and we first trained the random forest classifier. Then we found out the feature importances, and we sorted them in the order of the values, and the top n values where we have defined n equals to 20 have been segregated, and this is how we have found the selected feature names. So yeah, these are the ones which we see promising and more in correlation with the target columns. Post that, we also tried a few of models, machine learning models. We haven't articulated all the models which we have tried, but the ones which work quite well are here written. We found random forest, XGBoost, and light GBM to be working perfectly for this data set. The parameters which we'll be tweaking are also declared here itself with the respective models, of course. Now I like to invite Balaji to continue with this explanation.
Hey, this is Balaji again. As part of this project, we have done some of the steps. Thanks, Kaushik and Vinay. I'm continuing with the remaining steps we have done. In the step 6, we did the hyperparameter tuning, and then model evaluation, model comparison, future importance, and then model deployment. Hi, this is Balaji Kumresan. As part of our final project for this ML course, I have come up with a dashboard creation for the credit card data set we have identified. Here is the code, and let me share. Yeah, these are some of the dashboard reports I have created based on the credit card data sets we have identified. A box plot, strip plot, to use see the raw data with the box plot, and then histogram to identify the outliers and the multi-model data are high peaks, KDE plot to identify the misleading cases to estimate, and the violin plot for the smooth box plot with KDE is similar like KDE plot, and then counter plot to identify unique levels, count of levels, blanks, coded identifiers such as not applicable or 999 outliers, etc. I'm showing the dashboard generated here from each of for each of the different reports.